popping up, but I don't know in this system how to read them. Ah, chat. Yeah, I see a few. Should I read these ones?
Yes, sure. Please go ahead.
Okay, so a late question on the first part. In coupled point-like monopole-dipole approaches in electromagnetism, the problem is usually self-interaction, diagonal elements of the matrix, due to the fact that real atoms are not point-like, which are connected to difference between local fits. We have the same problem here. So that's a very nice question, actually. Okay, so this is only to me. So you don't read it. So basically, the question is, what is essentially the relation between this Willis coupling that we discussed actually both in the first and second part of my talk, and locality? That's a beautiful question. So when we describe the system as a monopole-dipole connection, we essentially approximate a finite size object with a point light. We concentrate all the response at one point, and we model that response as a monopole and a dipole at the center of the object that are radiating. The question is, how is this coupling between monopole and dipole connected with the finite size of the object, this approximation? And that's absolutely to the point. In fact, the original Willis paper that introduced Willis coupling, this coupling between pressure and velocity, indeed presents this phenomenon as a correction to the usual sound equations based on non-localities, on the fact that because the fundamental microstructure of our material is not point-like, there can be coupling between pressure and velocity that come from the finite extent of the microstructure. Indeed, the same assumption that our structure can be not mirror symmetric implies that the structure is of finite extent, cannot be localized at one point. Later, Milton, Bryan, and Willis reconciled basically this description with a local description. So that weak non-locality that is at the basis of this geometrical asymmetry can be still described as a point scatter with off-diagonal elements. So basically, the non-locality that arises that drives this coupling between pressure and velocity in acoustics can be still described locally, but with those extra parameters. In this talk, I also showed you that rotation of, as you see here, flow of mechanical flow in a geometrically symmetric cavity can induce a similar non-locality, but with an opposite phase compared to the geometrical correction. Also here, the non-locality inherent in this microstructure can be reconciled with a local description by using off-diagonal elements that are odd symmetric with respect to time-reversal symmetry rather than even. But still, it works. So it's a very interesting physics, by the way, of all of this. And are there other questions? There is another question here. So if there are no other questions, also Michelle wrote privately. In quantum field theory, you have C, charge conjugation, P and T symmetries that can be individually broken, but there is a theorem that the CPT cannot be broken. Do we have the same here? That's a deep question, and we are actually exploring these questions at the moment. In fact, it opens quite interesting opportunities in acoustics. There is a lot we're working at the moment. Probably it's not wise to dive too deep into this at the moment because we're still exploring some of these possibilities. But in short, yes, there are still constraints in what you can do, especially the limit in which these are still linear systems. One example, for instance, is the bound that I was discussing, that even in the limit, even when you break time reversal symmetry, the Willis coupling, the odd Willis coupling in the structures is still within that bound. But there are also opportunities that emerge here. One thing particularly interesting, by the way, in these structures, you see it here, is that when you hit the maximum Willis coupling, interestingly, the fields at the opposite sides of the cavity go to zero. For the the left side goes to zero for the pressure excitation, and the right side goes to zero for velocity excitation. This opens a lot of very interesting opportunities if you think now of introducing nonlinearities for gain and loss in these structures, and provides interesting tools that connect also to other open questions in the field of quantum mechanics and quantum field theory. Probably next talk, next webinar, we will have more on this. Anything else?
Hello.
Yes.
Hi, Dr. Alù. That was a great talk. Thank you so much for the very informative talk. I just had a very quick question for you with regard to your 2D method ratings and your the final final part that you spoke about with negative refraction. So across the 2D surface, is the loss and gain uniform, or do you distribute the loss and gain?
So your question is in this geometry here.
Yes,
exactly. Yes. Is this completely uniform, or these are made of atoms? Right.
Yes.
That's the question. Yeah. It doesn't really matter as long as the period between the distance between neighboring elements is below half a wavelength, because all the other diffraction orders would be evanescent. So that doesn't really matter as long as it's sufficiently dense. But in these specific simulations, both here and here, we are using a homogeneous surface. So it's yeah, the difference between these two, it's actually quite subtle but important, is that here we're assuming essentially a homogenized surface corresponding to an array of those loudspeakers that I showed you before, with less than half wavelength separation. The problem of that realization is that the impedance of that array depends on the angle. So for one angle, you get this nice negative refraction, but for other angles, you start seeing reflections and kind of like deviations from what you would expect from having a perfect balance distribution. That's simply because you remember that formula that the loss and gain must be twice the impedance of free space. The impedance of free space changes with the angle. The impedance is dispersive with the angle. So the array can be designed to meet that condition for one angle only, in the simple realization of just an array of loudspeakers. We corrected that problem by realizing this structure. There are actually a layer of metasurfaces. So not just one, but by having a few of them stacked close to each other, so transversely homogeneous, but longitudinally there is a stack of these metasurfaces, then you can make them to follow the impedance of free space for a certain angle. So now all angles in these simulations here obey that response. So the impedance of the array follows exactly the impedance of free space for each angle, and then you get the kind of lensing phenomenon that you would expect. So that's the sophistication. I didn't explain it in detail, but you can read it more in this paper here.
Okay, very interesting. Thank you so much.
Thank you.
Do we have any more questions? Please come forward.
I have a question related to meta-ratings. In the present investigations, the period D is a constant number. And my question is, would that perhaps be possible to enhance the properties of the structure if we assume that this parameter is not constant?
Sorry, the audio is not great. Did I understand correctly? You are asking about the period of the metagrading and what happens, what constraints it implies.
Yes. What would happen if period D is not a constant number?
Okay, excellent question. So in the metagrading approach, what we in the original papers that I was referring to, we were aiming at a specific functionality that we call it a test bed for metasurfaces. Basically, the functionality is beam steering. So you know the incidence angle of your wave, and you want to steer it to very large angles. If that's the functionality you want to achieve, then the approach we suggest is to choose the period to align one of the diffraction orders to the desired angle, and then engineer the unit cell to cancel scattering in all other angles. It's that allows you to go beyond the limits of gradient metasurfaces. Notice, interestingly, that the gradient metasurfaces, that sends the wave in the same direction with the continuous variation of phase of the reflection coefficient, has the same period as our metagrading, and that's the meta period, the period at which the phase repeats itself, and that's expected because that's what you need to get a diffraction order in that direction. Now the question is, what happens if that period changes along the surface? That's exactly what we've done now to show that the functionality of the metagrading in improving the efficiency goes beyond just beam steering. In beam steering, that D has to be constant. But imagine that now you want to use metagradings to focus, to build a lens. In that case, of course, that D cannot be uniform. Otherwise, you will not focus. You would just beam steer. But what we do is to build structures in which the period adiabatically changes. So it's still one meta inclusion per unit cell, but that unit cell structure changes gradually along the surface. And we've done that. We've built a meta lens based on this concept that shows very large aperture efficiency, in fact, close to 100%, based on this concept. So basically, each unit cell feels like locally it's periodic because the period changes slowly, and yet, so it sends the beam in the right direction, but that direction slowly changes with the position so that all the waves meet at the focus of the lens. So you have also that degree of freedom. And we have a recent paper with an experiment actually in Physical Review Applied, in which we showed, we call it a hybrid meta lens, because we use the gradient metasurface approach for the central part of the lens that does not have problems to work efficiently, but for the edges of the lens in which the wavefront transformation is extreme, especially for a focus close to the lens, we use the metagrading approach, and that combination allows you to get very large efficiency.
So do we have any more questions for Andrea? Especially, we did not have any questions regarding part 2, if I'm not mistaken. And I personally have many questions.
Sebastian?
Yes?
Thank you, Andrea, for the talk. Please, how much time does it take to reach this state regime in the negative refraction-based PT symmetry? Did you evaluate the time-dependent analysis similar to those performed for cloaking? And can we obtain the same behavior in the case of an incoming pulse, not a cosine pulse, a cosine continuous wave? Thank you.
Absolutely, excellent question. That's actually a very important question, and still there is a lot of work to do on this. I was mentioning about bounds for passive objects. There is a strict limit or trade-off between bandwidth of response of the response and typically size of the object. And so in a passive system, as the size of your object grows for cloaking or for these negative index responses, the narrower the bandwidth of the response. It means that it takes longer time for the transient to build before you actually observe it. And our studies show that with these systems, we can relax that bandwidth. So it means that the responses are faster. However, these are fundamentally limited at some point by stability. So the challenge is that can we have essentially an infinite bandwidth system based on this? Of course we can't, because as I was mentioning, the functionality of this system is that when we excite it from the left, the gain has to synchronize with the signal and start sending a signal identical to this that meets in phase here, and the two get absorbed by the loss. So it will definitely take some time before that happens. Interestingly, it's faster than what you would get from a passive metamaterial with the same thickness. Of course, it's causal, so it must, at the minimum, we need to wait for this to reach the gain and interact for a while before you start seeing this. You see, this is here a simulation of a finite pulse. And you see at the beginning, the clock starts scattering and then reaches steady state after a few cycles. But it's pretty fast, actually, it's surprisingly fast. Fundamentally, the speed at which that it takes before it reaches steady state depends on how close to the real axis the poles of the system are. And what we showed is that you can make them far enough from the real axis that this is still stable, but it's fast to reach the steady state. The challenge is that as the size of the objects grow, we have noticed that it becomes more and more difficult to keep the poles far from the real axis. And that physically makes sense. You need more time to let the wave interact with the gainy side and make them synchronize. So inherently, there will be a narrower bandwidth. But importantly, we don't know yet what is the bound. What we experience through multiple studies, in our papers, actually, this is discussed. We have papers devoted to this specifically. There is an evident trade-off between size and bandwidth over which the system is stable. And the question remains of what is the maximum possible bandwidth before you hit stability for a certain size of an object to cloak or a negative index length. It's for sure larger than what passivity gives you, but it's not necessarily infinite. I mean, for sure it's not infinite, yes. So a beautiful question to address.
Thank you.
Yeah.
Andrea,
yes.
Andrea, it's a bit of a mystery. What do you put inside your cloak, actually? What is it made of, your cloak?
In this specific simulation?
Yeah. What is it? Actually, it's a cloak in volume, or it's a meta surface? What is it, this cloak?
So this is a simulation, of course, and here we have assumed really an impedance boundary that has loss and gain, so homogeneous. We have another paper, actually, I think it's referred here, this one here, in which we actually designed a realistic surface made basically of antennas. So the object is surrounded by, I think, 8 antennas loaded with active and passive circuits on the two sides, and it does show the same effect. As I said, as long as the spacing between the antennas is smaller than the wavelength, so as the object grows, you need more antennas to cover it, then it works the same way. And we study there it's easier to actually study real stability, because we have a realistic circuit, a realistic system, and we can discuss clearly what is the stability limit.
There is this obvious question: could you apply this concept to thermal wave, to thermodynamics, to heat?
Yeah, that's a very interesting question. I would be very interested to discuss, and we have done many works together doing these analogies. That would be we didn't think about it. Of course, thermodynamics has some fundamental energy considerations, but here again we have gain, so it's not surprising you can beat those limits. Not in equilibrium, basically.
Yeah,
so it would be something cool to study.
Okay, so I think we all have thousands of questions to ask to Andrea, actually. So one way for you to keep asking questions, I guess, is to just email Andrea. And because, well, I guess that now it's been well over 1 hour. And so shall we close this webinar and thank again our great and inspirational speaker?
Very good. Thank you, everyone, and feel free to contact me anytime and for questions. And these are all great feedback already we got.
Thank you. And let me take this opportunity to remind you that our next speaker will be Professor Davida Bigoni from the Mechanical Engineering Department at the University of Trento in Italy. Okay, so thank you so much, every one of you, for attending this webinar, and don't hesitate to pass on the link, which will be made permanent so that people can actually enjoy as much as we did this talk. Thank you very much.
Thank you.
Andrea.
Thanks, everyone, Sebastian and everyone. Bye-bye.